Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. So this is, I get to spend an hour here doing something different from what I usually do and answering whatever questions you guys may have about science and technology. Try any kind of topic. If I don't know the answer, I'll tell you I don't know the answer. Let's see, we have a number of questions that got saved up from previous times. There's one from Wardrobe asking, do you think we will get anti-gravity cars? Let's talk about anti-gravity for a few minutes. So what is gravity? Gravity is fundamentally a force that is exerted by things that have mass. So the Earth, for example, has a bunch of mass, and it attracts, through gravity, things towards it. Now, there's sort of an interpretation of that is a bit more than 100 years old that comes from the general theory of relativity that says what's happening is that mass of the Earth is causing the very structure of space to be distorted. And that means that something which, if the Earth wasn't there, something might just, if you just started a spacecraft off and there was nothing in the way, it was just a vacuum, the spacecraft would just keep going in a straight line forever. Same with a beam of light. But if this force of gravity is associated with the fact that when there is something which has mass, it distorts the structure of space, it curves space, so that what counts as a shortest path, which would usually be a straight line, ends up being a distorted path that corresponds to something that will be attracted as it's the equivalent of being attracted towards the object. So sort of the big idea is gravity is the result of distortions in space having to do with the presence of mass. Mass causes a distortion in space. Okay, in the usual theory, there are only positive masses. Well, in the mathematical theory of general relativity, you can have a positive mass or you can have a negative mass. But in our universe, we only have observed positive masses. A positive mass produces an attractive force of gravity. A negative mass would produce a repulsive force of gravity. So, for example, if you wanted to make an anti-gravity car, you would need something which produces somehow anti-gravity that has the equivalent of negative mass. So there's a question of, can there ever be negative mass in our universe? Things we know, electrons, they have a positive mass, protons, they have a positive mass. The antiparticles of electrons, positrons, or the antiparticles of protons, antiprotons, they have a positive mass as well. They have their anti because they have the opposite electric charge, but they have the same gravitational charge, the same mass, both positive. So there's this question, could you ever have something with negative mass? Well, there are various detailed experiments that have been done on the expansion of the universe. And the expansion of the universe, when there is positive mass in the universe starts off in the Big Bang, starts off expanding rapidly, more or less the speed of light, actually, even in some sense faster than the speed of light in some theories that I don't think are quite correct. But the universe is basically, it's sort of a big explosion and things start going outwards at a certain speed. When there is mass in the universe, when there's enough mass in the universe, that the force of gravity will cause that speed to slow down. Eventually, the universe might stop expanding, might even contract again, and so on. Actual measurements suggest that the universe is not going to collapse. Instead, perhaps it's even expanding a little bit extra. It's like accelerating slightly in its expansion. So how do you get a universe that accelerates in its expansion? The answer is you put in something with negative mass in the universe. So that goes by the sort of brand name of dark energy in modern cosmology. And dark energy is basically negative mass stuff. And what is it? Does it exist? Nobody knows. But it's something which the experimental observations on the expansion rate of the universe suggests maybe should exist. Now you might ask, since we've been working on a fundamental theory of physics, how do things like negative mass show up in our fundamental theory of physics? Well, here's roughly how that works. So I've said gravity is a phenomenon associated with essentially distortions in space. But a big question in making a theory of physics is, what is space? And sort of the story for the last couple of thousand years has been space is just a place where things get put. There's no question of what space itself is. Actually, to be fair, in ancient Greek times, people did ask questions about what space itself is. But that kind of fell out of favor when people had kind of mathematical descriptions of just coordinates. You place something in a particular coordinate position in space. People stopped asking, what is space, so to speak? And the analogy I tend to use is, if you think of a fluid like water, you might say, well, it's just this thing that flows and you can have a little drop of ink anywhere in that water or whatever you want. And you might say, you don't have to say, you just have to say what the water does. You don't have to say what it's made of. But in fact, we know that water is made of discrete molecules. And so, for example, if we were to put that drop of ink or some smaller thing than drop of ink in different places around the water, there'd be some places we could put it where there's actually a molecule, and some places where we sort of couldn't put it because it's a space between molecules. So the question is, how does actual space work? And what we think very strongly is that actual space is not just this sort of background continuous thing where you get to place coordinates wherever you want. Instead, space is made of stuff. We call them atoms of space. They're really just idealized geometrical points. And what happens in our theory is that there's this giant number of trillions and trillions and trillions and trillions and trillions. I've got to say many trillions here to get the right number, 10 to the 400, maybe roughly, atoms of space that make up our universe. And all that we can say about these atoms of space is how each one is kind of connected to others. There's no sort of physically known connection. It's just an abstract idea of sort of a connection or relation between atoms of space. It's as if we know what atom of space is friends with what other atom of space, but we don't know anything else. We don't know how, quotes, far away they are or anything. We just know which one is related to which other one. So that giant collection of relations, connections, forms this giant network, and that is the structure of space. That structure of space is what happens is, just like water on a small scale might be made of molecules, on a larger scale it seems like a continuous fluid, so it is with space. Now, there's a question of, if space is like that at a particular moment in time, how does it progress with time? In our models, what happens is that locally in every little region of that network, if the network has a particular form, it gets rewritten to another form. It gets rearranged into another form. And that's happening all over the universe all the time. The structure of space, little pieces of space are being rewritten as other little pieces of space. In fact, if it wasn't for that rewriting activity, space would just fall apart. There wouldn't be any connection between different parts of space. It's that continued activity that kind of knits together the structure of space. And in fact, the structure of space, most of the activity of the universe is concerned with the knitting together of the structure of space. Things that we're used to, like electrons and photons and all those kinds of things, those are just little sort of ripples on top of this kind of all this activity of knitting together the structure of space. It's a little bit like if you have a fluid, and let's say you have a vortex, kind of a whirlpool inside the fluid, that's made of a whole bunch of molecules going around, but most of what happens in the fluid is molecules bouncing around, individual molecules colliding with each other and so on. That effect of the kind of the vortex is a very tiny effect relative to all the details of the molecules bouncing around. And so it is with space. The knitting together of the structure of space is by far the dominant effect. And the little sort of vortices or whatever else that correspond to the particles that we know about and pay attention to in the universe, that's a tiny effect on top of all of that. Okay, so most of the time, if there is, it turns out in our models, and it's one of the kind of spectacular things that comes out, is that we can understand that sort of additional activity in the structure of space is the equivalent of having mass or energy in space. And we can actually see the force of gravity emerges in our models. It's just essentially a mathematical, in a sense, computational consequence of the structure of our models. It's not something where you have to say, and then there is a law of gravity. That law emerges from the structure of our models. And essentially what happens is, when there is more activity in space, when there's more rewriting happening in space, that will be the equivalent of mass, and it will attract paths of things nearby in space will be attracted to that place. And that corresponds to the same kind of curvature of space leading to gravity that you see in general relativity. Okay, having said that, the question is, can there be anti-gravity? Well, what gravity is in our models is, in addition to all the activity to do with knitting together the structure of space, there's some additional activity that leads to the things like electrons and so on that have mass that we recognize. So the things we recognize, all of us, so to speak, are additional activity over and above the kind of background activity associated with knitting together the structure of space. So anti-gravity, negative mass, would correspond to places where there's less activity in the universe associated with knitting together than there would be from just the background of knitting together the structure of space. Do such things exist? We don't know. Is it theoretically possible in our models that there could be regions where the amount of activity knitting together the structure of space is reduced? Yes, it is certainly possible. In fact, in very extreme cases, in the center of black holes, where there are actual singularities in space-time, what happens in the center of the most standard kind of black hole is that in our models, I've talked about how space continually gets rewritten. That's the progress of time. There can be a situation in which there's just no rewriting that can happen. And in that situation, time effectively ends. And that's what happens in the middle of the simplest kinds of black holes, is you have a place where there is a structure to space, but time simply ends. And so in a sense, you can't really discuss, is space knitted together there, because time has ended. So that's a case where, in a sense, less is happening than you might think would be happening. In that particular case, time has ended. So is it possible that there are situations in which less will be happening in this underlying knitting together of space than usual? Yes, possibly, although I don't know specific cases in which that would happen. So that's kind of the foundation that one needs to make one's sort of everyday anti-gravity car. And we're certainly very far away from understanding how to hack space to achieve something like that. I actually wrote a thing last year about the question of whether you can travel faster than light in the universe, and that turns out that there is a way in which you can imagine kind of hacking space to travel faster than light. The only problem is that that hacking is happening right down at the level of individual atoms of space, which is a distance of a trillionth of a meter, very, very tiny, vastly, vastly tinier than anything that we currently know how to manipulate. But that's sort of a coming attraction for some number of centuries from now, perhaps, that it might be possible to hack the structure of space. Now, the real question is, let's say you hack the structure of space to go faster than light, which, as I say, I could explain how that works, but one can expect that that's probably possible. In some sense, what's really happening is that the structure of space has a certain typical form, but there will be places where you can have essentially these space tunnels, these fluctuations in the structure of space. And if you find exactly the right fluctuation, you can kind of hop from one place in space to another faster than a great big photon that's a piece of light could get through space. It's kind of analogous to the following thing. In air in this room, it's a bunch of molecules bouncing around. The typical molecule goes only a tiny fraction of a centimeter before it collides with another molecule, which then randomizes its direction and so on. But if you could pick the exact right sequence of molecules to ride on, so to speak, you would be able to go from one side of the room to the other at basically the speed of sound. As it is, the molecules will bounce off each other, they'll bounce in the wrong direction, they'll go in this way, they'll go that way. It takes a long time for something to diffuse from one side of the room to the other. But if you could kind of hack the molecular structure of the air, you could actually go pick the correct molecule to just ride on to get from one side of the room to the other, and you could do that at the speed of sound. So it's the same kind of idea in hacking the structure of space. But one of the issues is, okay, you're down at the level of individual atoms of space and you're hacking things, so to speak, but how do you get a thing like us down to that level? You know, it's all well and good to say, well, we can get this little tiny spacecraft that consists of 3 atoms of space or something to make the jump faster than light to somewhere else. But if we're trying to go faster than light, that's a whole different story. We're very big on the scale of the atoms of space. And it's sort of analogous to the following thing. If you imagine that you say, well, I want to take a trip to a nearby galaxy. How am I going to do that? Well, there's a way to get something to make a trip to a nearby galaxy. You just shine a laser out into space, and maybe a photon or two from that laser will just keep going and keep going and keep going, and eventually we'll get to that other galaxy. The way things work, when you go at the speed of light, you're kind of using all your computational effort to move. And none of your computational effort goes into the elapsing of time for you. And so time stands still. That's a phenomenon that was discovered in relativity theory. It's something which we now have a very sort of straightforward understanding of in our models of fundamental physics. But essentially, if you're riding on that photon, time is standing still for you. So then the question is only, you say, well, that's a great way to visit the nearby galaxy. I just hop a ride on a photon. The only problem is it's profoundly not you by the time you're reduced to a single photon. So there's sort of this trade-off. If you want an observer of what's going on that's kind of like you, then it's tough to stuff that into something like an individual photon. So this is a complicated trade-off. If you want to have a thing like you that kind of experience, I don't know, moving across space at a certain speed, then that's something that is a much different challenge from just saying, is there anything that can propagate across space at that speed? Okay, let's see. There was a question here from Erin. How much memory does a rock have? Do protons or photons have memory? Do orbits have memory? How much memory does a rock have? Well, here's a funny thing to say. A semiconductor device, a chip, a memory chip in your computer. What is a memory chip made of? It's made of silicon. Silicon is basically the main ingredient of rock. So in some sense, when you have a memory chip, it's a very, very carefully refined piece of rock. And so that memory chip is effectively like storing information in something like a rock. It's storing information in the configuration of electrons that exist there. Now, in a naturally occurring rock, you also have configurations of electrons. There's a question of whether there are many different configurations that can all exist in that way. The rock could be set up that way. The big idea of, for example, a magnetic disk. Okay, let me explain a little bit more here. So in magnetism, what is magnetism? If you have a bar magnet or something like that, what actually is that? Well, there are elementary magnets. Individual atoms of iron, for example, have the feature that they, the ultimate individual sort of elementary magnets are things like electrons. Electrons fundamentally are like little tiny bar magnets. They have a certain magnetic field that they produce. And so, you can align an electron, the electron spin is what determines this direction. You can align an electron to produce a magnetic field that's like a bar magnet with its north-south orientation being wherever you want it to be. So what you're doing when you have a bar magnet, is you've got lots of little electrons that are part of iron atoms and so on, that have all lined up to be all in the same direction. So they're all their magnetism is adding up together, and you get this thing with a big magnetic field that corresponds to a bar magnet. Okay, so that's what's called ferromagnetism, is when you have a situation where all the electrons can keep themselves all lined up. There's another thing called ferrimagnetism, where you can have little tiny domains where one part of the material has all its electron spins up, another one might have all its electron spins down, and so on. And you can have in very sort of fine regions, not individual electrons, but just small numbers of electrons where everybody's lined up one way, everybody's lined up another way, and so on. And for those of you who remember magnetic tape or floppy disks and so on, or even hard disks, those are ferrimagnets. Those are things where there are local regions of a material that are magnetized one way or another way. And that's how the data is stored on something like a floppy disk or a physical hard disk. Nowadays, because of sort of an abusive notation, people call things hard disks when they're actually made of semiconductor memory. But back in the day, when one always had these spinning disks, they were made of ferrite, and each little region of the disk will be magnetized one way or the other, representing a 1 bit or a 0 bit at that particular place on the disk. So whenever you have something like a ferromagnet, and there are plenty of minerals that behave as ferromagnets, you can have something where you've got I'm distracted here because I realize there's a ladybug crawling on my camera. I don't know whether that's a sign of good luck or whatever. Let's hope it is. Anyway, back to this. So we've got in something like one of these minerals that can have little magnetic domains pointed one way or another, you can certainly store information. So can you probably store information in the detailed structure. For example, actually, here's a better example. If you have a perfect crystal where all the atoms are perfectly lined up, there's really no information in that crystal other than just you've got a crystal and everything's lined up. But as soon as there are defects, places where the crystal doesn't have all its atoms perfectly lined up, those defects can store information. Now, it may be more or less difficult to actually extract the information. For example, people often have cases where, I don't know, you can write data in you can etch things into quartz. You can have these things called bubble memories where you're putting magnetic bubbles into materials and things. In all of these cases, you're kind of trying to change the structure of the material to store memory there. Even in our brains, most likely the synapses between nerve cells, the way that they store memory is through the calcium channels that exist that either do or do not permit signals to go through between different nerve cells. And those channels, it's as if we're just sort of putting little pieces of rock, little pieces of calcium-like stuff into the 100 billion synapses in our, no, the 100, it's more like million billion synapses in our brains. 10 to the 14 synapses, I think, which is about 100 trillion synapses in our brains. Each one is kind of like a little tiny piece of rock at some level storing memories there. So the challenge is usually the structure of a material, all the detailed configuration of its atoms can represent the storage of information. The challenge is how do you write that information to the thing and how do you read it out again? Now, this question asked also, do protons or photons have memory? The answer is not much from what we know. It seems to be the case in current theories of quantum mechanics and so on, it seems to be the case that there's only a limited amount of data associated with each individual elementary particle. In particular, the only things that one knows about elementary particles are their momentum and energy and their spin direction. Those are the only things that characterize elementary particles. Now, it's a weird fact that there's one other thing in the universe that kind of works that way, and it's black holes. Black holes, you kind of can only characterize them by their total mass, their momentum perhaps, and various attributes about their angular momentum, essentially their spin. So it's kind of a funny coincidence that this very big thing, black holes, this very little thing, these particles, are both characterized by this limited amount of information. Kind of makes one wonder whether they're actually the same thing. And I remember when I was, I don't know, probably 14 years old or something, I went to a talk given by some well-known physicist who was talking about black holes a long time ago when black holes were just sort of first really being discussed seriously, and was talking about this and talking about particles and all those kinds of things. And I went up to him afterwards and I said, based on what you've said, is it possible that particles are just very tiny black holes? And he's like, oh, no, they couldn't possibly be true. They're totally different areas of physics, no connection whatsoever. It'll be interesting if it turns out that 50 something years later or whatever, that turns out to be what actually happens. And I think there is some evidence that there is a close connection between the way that black holes are made from the large scale structure of space and the way that particles might be made also from the structure of space. Because, an electron in our models of physics, an electron is still many trillions of atoms of space across. It's actually pretty big on the scale of what happens in the universe. Now, your average black hole might be an awful lot bigger because it might be the size of a star or something. It might be kilometers across, might come from a whole star or something. But the fact is that the way in which you get these sort of discrete kind of, let me explain. There's this kind of idea of a topological obstruction. So for example, let's say you have a piece of string and you've got it, it's wiggling all kinds of ways. You pull on the ends of the piece of string becomes taut, it's just a straight line. Okay, let's imagine that the string is wrapped around a pencil somewhere. Then you pull on the ends, and pull as you might, you'll never untie that the string is always wrapped around that pencil. You can think of it as sort of a topological feature of the string. It's kind of wrapped around something, and however hard you pull, you're not going to be able to unwrap it. The same thing happens in something like a vortex in a fluid. What's happening is the pieces of the fluid, the molecules in the fluid, and on average are going around in circles around that vortex. And sort of, even though the vortex is buffeted from all sides, you kind of can't get rid of that kind of, the fact that it's swirling around that thing. The same reason that a tornado is fairly, or a hurricane is fairly stable in the Earth's atmosphere. You have to kind of do something that kind of jumps over that sort of singularity in the middle to be able to get rid of the thing. And that kind of persistence, that sort of topological stability, is what is sort of at the heart of why black holes work. It's also perhaps at the heart of why particles can exist in space. So those might be the same kind of thing. Okay, if that was true, what would it mean? See, a black hole, all you know when you see a black hole from the outside is kind of what it looks like from the outside. If you go near the black hole, you fall into the black hole and you're never heard from again. So in a sense, the kind of what we know about a black hole is only what its exterior, its boundary shows us. And so there might be all kinds of things going on inside the black hole. You know, there could be all kinds of spacecraft that have fallen through the black hole and everybody's partying inside and they're having a grand old time. And, you know, they've made a whole civilization there and they've got, time is progressing perfectly well. Time will eventually stop in the black hole. That's, you know, that's kind of well, that's a weird situation because when time stops, you don't know that time stopped because time has stopped for you. But but things could be happening inside the black hole. But from outside the black hole, there's an event horizon. We don't get to see into the black hole. We don't get, nothing from inside the black hole has any effect on anything outside the black hole. So it could be the case the same thing happens for particles. It could be the case that in a sense, inside your average electron, there's more stuff going on. And it just, one of the things that's really a mystery about electrons is they're all the same. That's a fundamental fact about quantum field theory, particle physics, whatever you want to call it. All the electrons in the universe are basically the same. They can have different momenta, they can be going at different speeds and things, and their spin can be oriented differently, but otherwise they're all the same. They all have a mass of, you know, 0.511 MeV, et cetera, et cetera, et cetera. They all have these same characteristics. Why is that? Well, could it be the case that from the outside, so to speak, they all have the same characteristics, but were we to be able to sort of bore into the electron, they would be different inside? We don't know. And in the idea that kind of electrons are a little bit like very, very tiny black holes, there is a sense in which there might actually be sort of a different structure inside different electrons. And that has a bunch of implications for all kinds of questions about quantum mechanics and so on, although it is less important than you might think because we are observers who only are sensitive to things like what's the exterior of the electron like. So anyway, the answer is, I suspect in current theories of physics, no, you can't store very much information in a single electron. You know, it's possible that if you were to sort of, if you were to be able to fall into an electron, you might find all sorts of other stuff there. But even if you did that, you might never be able to get out and tell anybody on the outside. So in a sense, it's not useful to have thought of one having stored information inside there. Let's see. Oh boy. Oh, there are many, many questions here. They're very interesting. All right, let's talk about it's a question here from Mr. When is someone considered dead? How do we define the line between alive and dead? You know, I'll tell a sort of a parable type story. So in theory of quantum mechanics, there's all this question about whether you only know the probabilities of things or whether definite things happen. And a chap called Erwin Schrödinger had this idea of kind of illustrating sort of a thought experiment about quantum mechanics. And he said, look, you know, you have all these probabilities and things, but if you have something where you have a cat in a box and the poor cat has some lethal thing pointed at it, then in the end, the cat is either alive or dead. And it's kind of, for him, it's kind of, you can't say, well, there's a certain, the cat is kind of 90% alive and 10% dead, or, you know, it doesn't work that way. If you imagine some small physical system, like you said, this is, I don't know, I don't know, something is there's water that's boiling, and you know, some of it is a little bit boiled, but a little bit not boiled, but it could condense again, and there isn't so much definitiveness about the water is either turned to steam or it hasn't, because you know, the steam could have droplets in it, and it could be kind of a gray area in between. But the traditional kind of, you know, when you think about a cat, it's either alive or dead. And when you look at lower organisms and you say, is that kind of tardigrade, water bear, little tiny organism, is that really alive or dead? It's hibernated. It's on the moon. I'm embarrassed to say a friend of mine was responsible for actually sort of somewhat inadvertently spilling tardigrades on the moon. As a result of putting a sort of payload on of kind of interesting materials from our civilization onto a spacecraft, which unfortunately crashed into the surface of the moon a couple of years ago now. And one piece of what was put in there was a little package of tardigrades, which were strewn presumably over the surface of the moon on a small area. But the question is, are they alive or dead? They are at best hibernating. All of their processes have slowed to nothing, but probably if you put them in water again or something, they would come back to life and be happy and say, what happened over the last 1,000 years? I didn't notice the passage of time over the last 1,000 years. Now, when it comes to us humans, there are just all these systems that work inside us, and they are all connected together. And if you fundamentally stop them, if you fundamentally stop delivering oxygen to tissues, you stop the process of metabolism, tissues will die, and tissues don't come back to you know, they don't, they actually die. What does it mean to actually die? It means, you know, we have cells, they've got these elaborate machinery in them that are proteins that are kept in some particular state. And if they die, it means it's all scrambled up. The proteins are no longer arranged in these nice forms. They no longer things are no longer sort of sliding around and having all the chemical reactions they're supposed to have. Instead, they've been sort of, you know, they've been all scrambled up. And in fact, often in organisms like us humans, cells undergo this thing called programmed cell death, apoptosis. And so when a cell thinks that it sort of should die for the sake of the organism, the cell will release these little packets of essentially poison inside the cell, lysosomes, that will cause the whole cell to kind of self-destruct. And that's what happens, for example, in cases where the immune system is going to attack cells that are infected with viruses and so on. What will eventually happen, well, there are a bunch of different processes, but one of the things that can happen is the cell is kind of given the signal, just self-destruct. The same thing can happen if cells are deprived of oxygen, things like that, that cells go into this pattern where they destroy themselves. Now, this question of sort of what counts as an organism being alive? Well, it's that all of its standard processes are running, running as they should run. What are the indicators of that happening? There's things like metabolism, that is the sort of the continued use of oxygen to sort of do these little microscopic kind of burning processes that are what generate energy for our cells, all those kinds of things. There are also things for humans like brain activity that we can measure, things like that. Now, when you ask the question, are you there, so to speak, that is also a question of, is the brain doing the things it should do to have you be conscious and kind of aware of what's going on? That's a more complicated issue, because you can imagine a situation where there's, of the 100 billion neurons in your brain, there are lots of neurons that are still firing and doing things, but somehow you haven't synthesized that together to make this sort of thread of experience that we associate with consciousness. And in fact, the brain seems to have very definite mechanisms for maintaining that sort of thread of experience. There are particular, if you talk to neurosurgeons, they'll tell you, if you've damaged the such and such cranial nerve, then you're kind of out of luck. You don't seem to be able to synthesize that kind of thread of experience that's associated with kind of our typical conscious experience of the world. So there's sort of very detailed properties of the brain that seem to be necessary to synthesize kind of our view of the world. It's kind of as if you could say, well, I've got a little piece of brain tissue here and it's got neurons firing and doing things, but it's not really aware of the world, because it doesn't have this kind of notion of a thread of experience that we seem to have. Now, could you imagine that it's like an alien species where you've got a little piece of brain and it's having all kinds of things happen in it? It's having sort of, quotes, thoughts, but they're not thoughts that we can align with our usual notion of kind of conscious experience. So that gets a little complicated. And I think that this question of kind of under what circumstances, what does it mean to, that there are other things with humans of how much is a human sort of independently able to be walking around, sort of doing things independently, and to what extent do you have to have technology that is serving the place of various kinds of human organs and those kinds of things. And that's another sort of criterion for whether it's a kind of a complete live human and so on. But my guess is that in fact in the future that this border between the sort of what's fully alive and what's not and so on, it's going to get more and more complicated. And I think the one thing that is really seems to be a dividing line is this kind of thread of experience kind of idea, and whether that's being maintained or not. And the question of what happens when that thread of experience can be converted to something which is essentially a digital version of the same thing, where the main sort of activity of the neurons is being driven not by other neurons, but by some technological device, then this becomes a very complicated question. So I think that's about as much as I could say about that right now. I think that this whole question about whether, in some sense, this sort of, is the organism dead or alive? For typical big organisms and typical situations, that's very sort of easy to answer. But it gets a lot more complicated. Like, for example, let's imagine that we could freeze an organism. Right now, what happens if you try and freeze something the size of a person, there's this horrible problem that water is fairly unique in this respect. It's a substance that gets bigger when it freezes. Ice is of lower density than liquid water. In other words, for a given mass of water, as ice, it occupies larger volume than it does as liquid water. And so that means that when you freeze something with lots of water in it, as we have, then things will expand. And for us, that will be really bad news, because our cells will just explode because they have little pieces of ice in them. And so, there's a whole bunch of technology. When you get water down to a sufficiently low temperature, I think it's 44 degrees, minus 44 degrees Celsius, you end up getting into this kind of glassy state that's a form of solidified water that isn't like the crystalline structure of ice, and it doesn't have this property of getting bigger. But eventually there might come a time when you can like freeze organisms, and there are some kinds of fish that successfully get frozen over the winter, in ice. And there's sort of the question: is the frozen fish alive or dead? The frozen fish is really frozen, like nothing's moving. It's a solid. It's not, a lot of what makes us work is we're very liquid state creatures. It's not quite liquid, it's more like a gel, but we're using the fact that we can have these sort of flowing materials inside cells and so on. If we're like frozen solid, none of those processes work anymore. And there's the question of, is the frozen fish alive or dead? And I think that's a complicated question of what you choose to make the words mean. The fish can be, when you heat the fish up again, it's a happy fish swimming around. If we're lucky, that might be possible for humans too at some point. All right, let me see. Question. Let me see. Well, okay, there's a question here from 0D. How do a flock of sparrows know how to change directions simultaneously? So, it's a feature of flocks of birds, schools of fish. You see this big collection of birds, and they're all going in one direction, and then they change direction, start going in a different direction. Same with schools of fish. How does that work? Well, there's what seems to, the best we know about that has to do with models that can be made, computational models that can be made. There's a class of models called BOIDs, B-O-I-D-S, that invented by a chap called Craig Reynolds, originally for making things like flocks of bats in movies. And I think it was a Batman movie that was, I'm not sure if that was actually the first one, but was certainly one where BOIDs were used. So how do these computational models work? Well, the idea is you have a bunch of organisms, and each organism kind of can see to both sides of the organism. And then all it's doing is it's looking locally around it at who's nearest to it. And then it's sensing kind of what those nearest things near it are doing. And it has a couple of parameters about sort of how much it tries to align its direction with the directions of its neighbors and so on. But essentially, what's happening is it's a little bit like what happens in a magnet, for example, where all the electrons eventually line up. As soon as that bird likes to be aligned with its neighboring bird, you've got sort of a force that tends to make all the birds turn together. Now, depending on how you set up the parameters, it turns out there's a large range of parameters where fundamentally the flock of birds is going to stay together. Now the question is, what makes the flock change direction to begin with? Well, there's typically a lead bird, and I don't know what causes the lead bird to suddenly say, I'm fed up with going in this direction, I'm going to change direction. I don't think that's known. And it's an interesting question. What is the sort of generator of randomness in the brain of a bird or a fish or something that causes it to suddenly decide, okay, time's up, I'm going to change direction? There are some mechanisms in brains that are understood about how sort of decisions get made. So very, very simple example, walking, for instance. It's a pretty low level function inside brains to keep the legs walking back and forth. You don't need sort of elaborate conscious thinking to be able to do that. It's kind of like you can just, without really thinking about it, if you're on a treadmill, or even if you have some terrible experiment with an animal where most of its brain isn't there, it'll still walk on the treadmill, so to speak. And that, it's usually called in the kind of literature of these things, the central pattern generator. It's a kind of a circuit made of neurons that actually has this property that it is generating this kind of wave of activity that just does one left foot, right foot, left foot, right foot, and so on. So that's a case where it's kind of known what the kind of neural circuit that leads to activity is. There's probably something like that that is the sort of generator of randomness that leads to that, oh, time's up, I'm going to go in this different direction, but it's not known what that is. It's actually one of the weird features in terms of birds is, how do birds know which way to go? How do pigeons know how to go home? Things like that. I remember years ago, there was a funny paper that I think is correct, that basically says, in the end, pigeons often remember the pattern of roads, and that's how they're sort of following the roads to figure out how to go from here to there. Presumably before there were roads, they were following other kinds of landmarks. Pigeons actually seem to have another weird feature, which is pigeons directly seem to sense the Earth's magnetic field. So, the Earth, that's how a compass, a magnetic compass works, is the Earth has a magnetic field produced by currents in the Earth's mantle that has so the compass needle will align itself with the direction of the Earth's magnetic field. And it turns out that pigeons seem to have a direct mechanism, a direct sort of organ in their brains that can sense magnetic fields. And it's becoming a little bit clearer how that works. And it's kind of a tricky thing. It is a thing that depends very much on having individual atoms that will align themselves to the field whose little spins will align themselves to the direction of the Earth's magnetic field. And there's a whole mechanism to sort of read out the this very detailed kind of atomic scale feature of these atoms. Essentially, what's happening is normally the spin direction this is let me think about this for a second. This is usually the direction of the spin has no direct effect on things about chemistry. It has an implicit effect because that's what causes one to be able to fill up electron shells and things like that for chemistry, but it has no direct effect. And what happens is there are these situations in which one seems to have a direct chemical effect of spin directions through particular structures of molecules and so on. And that's what seems to happen in the brains of pigeons. Let's see. Okay, there's a question here from Quantum. Do I think it's more important for humanity to look to colonize another planet or to look after the Earth and make it more habitable in the future? I do have to say that one of the things I think people get a little bit confused by is if you look at the history of Earth, its climate, for example, has changed dramatically over the years, over very long periods of time often, but even shorter periods of time. Even in the 1600s, there was a little ice age. And places where it's pretty warm in the summer nowadays were very cold all year round, even in the 1600s, so not long ago. And there are these cycles that are to do with the Earth's orbit. There are other cycles. There are a variety of their cycles, perhaps even in the amount of radiation produced by the sun. There are all kinds of things that affect things like the temperature of the surface of the Earth, the amount of oxygen in the Earth's atmosphere, the amount of carbon dioxide, et cetera, et cetera, et cetera. We humans are having an effect on all of that. Whether our effect is large compared to what is naturally there, well, that's a whole complicated debate, but assume that it is fairly large. It's still the case that one can expect that the climate of the Earth and so on will change over time. The question is, what do you do about it? And you can say, well, I want to turn back the clock. I want to make the Earth be just like it was when dinosaurs were around. Probably bad for us. I don't think I forget what sea level was like in the time of the dinosaurs, but things were very different then. And I think it's one of these things that I've sort of wondered, why are people in the past, a millennium ago, whatever else, there were these changes of climate and all kinds of things on the Earth. why did people seem to make less of a big deal out of that then than now? Well, part of the answer is that, if things change over 100 years and you're farming one piece of land and you're basically kind of nomadic and now you're going to farm another piece of land, it isn't that big a deal. If you've built a very fancy city and with all kinds of skyscrapers and it's right by the ocean and it's beautiful beachfront property and so on, and suddenly sea level, not suddenly, over the course of 50 years, 100 years, 200 years, sea level changes, then it's like, oh my gosh, my skyscraper is not going to be worth as much, or is going to, have to have a dike built around it or some such other thing. And, in a sense, by building up all of the things we have in the modern world, we've made things a bit more fragile than they were before. And so that's kind of it's a feature of progress that's happened. One can have all kinds of discussions about, okay, well, we've got that kind of progress. What about doing geoengineering to, change the effect of this or that or the other on the Earth? What do we do to sort of change what, whether we put more carbon dioxide into the atmosphere or don't? Clearly, there are, better. One of the things that's a bit confusing about modern sort of questions about this. There was a time, when was it? In the 70s, I guess, 1970s, when there was this problem with ozone, which is what blocks ultraviolet light from the sun. There was this sort of hole in the ozone layer in the upper atmosphere that was developing that was traced to being associated with the kind of propellants, CFCs, that we used for aerosol cans. And so people said, let's get rid of CFCs and use something different for aerosol propellants. And by golly, that had exactly the effect you would expect. And, the ozone hole, I think, disappeared and everybody was happy. Turns out it's more difficult. It seems to be more difficult to get rid of some of these other things that are sort of random side effects of technology. Maybe there'll be ways found to get rid of those more easily and it won't be a big deal. But if it had been the case that people said, okay, no more aerosols, that will be, no more spray cans of anything, that might not have been a good thing. There are plenty of medical purposes and so on for which those are used, and that would be bad. But it turned out there was an alternative technology, wasn't so difficult to implement, and so all was good. But so, there's this sort of question of, what technological solutions, it's a side effect of technology that things are happening. There's something that's going to happen anyway. We have to kind of decide, how do we feel about sort of the Earth changing anyway? Are we going to say, no, we want to lock it down? The Earth as it was in whenever, pick your date. I want the Earth to always be that way. Well, actually, we'd have to really change what's happening in the Earth. I mean, for example, the rotation of the Earth is slowing down by, milliseconds per year or something. And it's like, well, that will mean that at some point, the length of the day will be measurably different. Oh, we could say, we don't like that. Let's speed up the rotation of the Earth. Kind of why? Why bother? Turns out it doesn't seem to matter much to sort of everyday life. There are things that do seem to matter more to everyday life, and those we might care more about not having sort of go out of kilter. But that's sort of a trade-off, because if you say, well, in order to get the way that we want the Earth to be, we need to do all these elaborate things. I mean, it's kind of like there are things we want to do to kind of lead our lives that are enabled by technology. There are things that there are side effects of that technology. We can fix that and so on, but we kind of have to decide how much we want to sort of distort the things that we have been made able to do for the sake of things where we don't even know necessarily what the consequences are going to be and so on. So, complicated issues. But, the best situation is when it just turns out it's an easy technological fix. And perhaps we'll get more of those. Perhaps we'll get fusion power, for example, which will be an easy technological fix potentially. I remember when I was a kid in England, one of the things that was an issue was there had been a lot of pollution around cities. There still is in many countries. There's lots of pollution around cities from power plants and so on, and factories belching out stuff into the air. Well, people said, no, you can't do that. Put filters and et cetera, et cetera, et cetera. And it turned out what just wasn't that difficult to do. Similarly, to clean up rivers and so on by by putting filters before you dump stuff into rivers. And it turned out in a period of a decade or two, things became, it was no longer polluted in London. It was no longer, the Thames River was no longer a totally polluted thing. That was comparatively easy technologically. And it wasn't oh my gosh, to achieve this technologically, we have to completely change the quality of life, so to speak. So, one can, I think an important place to push is on these sort of technological fixes, which may be obvious, may be easy, may not be so obvious, may require more technology to achieve, and so on. And also to ask the question, what is it that one wants to achieve in the end? One of the things that we may be able to do eventually, people have been wondering about this for forever, is can we control the weather? Can we control local weather? Like, it rained where I am today. And I really wanted to go for a walk. Could I have, pressed some buttons and made it be the case that no, it wouldn't rain where I am, and it would be controllable. But the question, if you say you control the weather, is okay, but the weather, it's not just about me going out for my walk. There's lots of other people who live near here too. And, how do they feel about what the weather should be? It becomes a very complicated question once you can make these kinds of changes that have sort of a global effect. How do you make the decision about what to do? And then it becomes a complicated kind of socio-political question. But the question is also, what about colonizing other planets? Well, one of the problems is that we humans, with the particular biology we have, we just spent 3 billion years evolving for this particular planet that we're on, with all its various changes and ice ages and this and that and the other, but fundamentally we're evolved for this planet. And if you say, okay, let's go even to Mars or Venus, the planets are different. And maybe we can terraform, maybe Mars, maybe Venus. We can make it so that those planets will have atmospheres somewhat similar to our own, although their gravities will be slightly different because they're different sized planets and so on. It's an interesting question. Again, if you say, it's the ultimate kind of environmental effects question, you say, we shouldn't build a city in this forest because we'll be destroying a bunch of forest. You say, should we build a city on Mars? And should we change the whole atmosphere of the planet Mars to be more human friendly? Well, you might say it's just a piece of rock. And so far as we know, Mars is just a piece of rock. There's no life there. There's nothing we think is important, but there is rock there. Right now, we don't have any qualms about saying we'll change the environment for the rock. If there was a life there and we had little creatures crawling around, we might say, look at those cute little creatures crawling around on Mars. We don't want to destroy their habitat. We don't right now. We have no evidence for life on Mars, at least right now. And recognizing what life is and is it similar to life on Earth, that's a whole complicated issue in its own right. But this whole question about, do we feel that we should go and just change the universe? Well, we're changing the universe locally here on Earth, so there's an argument, why not just extend that and start changing it on other planets in our solar system or whatever. But assume we did that, and that's a very difficult thing to do, not obvious whether it would work, not obvious how to do it from a physics point of view, and so on. There's still, it's still going to be a big nuisance, let's say, to live on Mars, just as, people don't live under the oceans because it's a big nuisance to do that. People don't live, in Antarctica because it's a big nuisance to do that. We are evolved for those areas of our planet where we've been evolved to live. And to get to a different place with our current evolutionary characteristics, with our current biological characteristics, is not an easy thing to do. And you might say, well, gee, over a sufficiently long time, why don't we just evolve into a different form? But then it's kind of like, well, what are you trying to achieve? I mean, by the time you have the computer that is running a digital version of me that's sitting in a co-location facility on Mars, it's like, what have we exactly achieved here? Is that really a direction we want to achieve? All right, I probably there's a question here about, can we push jet streams on the Earth? The jet stream is this high altitude rapid wind that goes around in the northern and southern latitudes. And there's the sort of question of what aspects of the Earth's atmosphere and the flow of air in the atmosphere are somehow unstable. What fraction of those things are very robust, and whatever you do, you can't really perturb them, and which ones are sort of sensitive. And if you could just put the right thing in the right place at the right time, you would suddenly flip that ocean current or that current in that wind stream of wind in the air to go in a different direction. I don't know, and that's an interesting question to ask for climate models and things, to what extent there is stability. Those will be difficult questions to answer, because the way these models are set up, there's a big issue of validating the models, and there are questions about stability of the underlying methods that are used on a computer to make those models work. And probably a certain amount of hackery is being done there, but I know it's being done there to that will make it a little bit difficult to answer these sensitivity questions. But it's an interesting question. I don't know the answer for the specifics of actual current climate models. All right, I had better go now. I have something else I have to do right now. But thanks for those questions. I see we have lots of interesting ones queued up, ready for same time next week. Look forward to seeing you there.